Let's begin. We're going to talk today about ocean tides. Ocean tides. I got a question for you. The tides are influenced by the moon. The tides are influenced by the sun. Which plays the greater role in raising tides, the moon or the sun? What is it? The moon. I got a different question for you. There's a force of gravitation between the oceans of the Earth, and the moon. There's also a force of gravitation between the oceans of the Earth and the mass of the sun. So both are pulling. Which do you suppose pulls harder on the oceans of the Earth, the moon or the sun? How many say the moon? Stand up. How many say the sun? How did you guys know it's the sun? How do you know? Where did you find it? How could you not read the chapter and be astonished by that? I always used to think that the moon pulled harder on the oceans because it's closer. And the sun's so far away that the pull is a lot less. That's what I used to think. And then I get into my physics and boom. Sometimes in physics you find things that are kind of like counterintuitive. Don't they kind of say, hey, wait a minute, what's this, huh? And what's going on? It turns out that sun is far away, but honey, it is big. Let me put it this way. You know the sun's hot. And when you step from the shade into the sunlight, you can feel the heat of that sun, right? And you might say, wow, I can feel the hotness because the sun has got such a high temperature. But you know what, gang? I can bring you to welding shops wherein the torches of some of those flames are hotter than the surface of the sun. Hotter. And you walk by that welding shop and you don't go like that. But you step from the shade into the sunshine, whoo, you feel it. It's not that the sun has a high temperature. Do you know why that sun's so hot? Because it's big. I mean big, big. Very, very big. But it's far. But it's bigger than it is far, and it pulls on the Earth's oceans more than the moon. So how come we get, then, the tides by the moon? And the person to figure that out was named Isaac. Guess what the last name is, gang? How many people not be knowing? Isaac Newton is the one that figured that out. Let's suppose we have a ball of putty, or a ball of taffy, or a ball of Jell-O. Something that's really pliable, something that you can wang around a lot, okay? And let's suppose I pull it across the room, and I pull it everywhere with just the same amount of force. What it would do is it would race across the room. And when it got here, if you took a snapshot of it, it would still be in a ball shape, okay? Let's suppose instead that I pulled on that Jell-O a lot stronger here on this part, and so in the middle, and over here a little bit weak, quite a bit weaker. Now I have a difference in pulls across the Jell-O. That Jell-O, gang, is going to race across the room. But when it gets over here and you take a snapshot of it as it goes by, would it have that shape? No, it wouldn't have that shape. Because this side here is accelerating more than this side. It's a pliable stuff now. So this side here would maybe get out to here. This side here is not being pulled so far. That would lag behind over here. And so what would happen to the shape of the Jell-O, gang? It would be kind of like this. It'd be kind of stretched out, wouldn't it? And guess what behaves the same way? Begins with O and ends with shun. Try it. The ocean of the Earth. Because it turns out this is our Earth. Here's the moon over here. The moon's pulling this side harder than it's pulling this side. Why? The answer is easy. Check your neighbor to be sure we're all there. Why is this side being pulled harder than this side? How many say because this side's closer? It's closer. When you're closer, the gravity's stronger. Hey, no big deal, huh? And that's right. So this side's being pulled out into a shape, and this being left behind. Now, is the Earth really moving toward the moon? We on Earth think, no. The moon is moving toward the Earth. there's a force on the Earth. I mean, there's a gravitational force between the Earth and the moon that pulls the moon this way, right? Why don't the moon crash? Because it's moving like that. So as it's being pulled, instead of coming over here, it's moving like this. So it doesn't get to here, it gets to here. It's being pulled like that. Instead of getting to here, it gets to here. And so it gets pulled around and around and around in a circle. But guess what the direction of the acceleration is as it's going around and around and around the circle? Toward the center of the Earth. See? So we think of the moon as going around and around and around us. Like I take a rock on the end of a string and I go whirl it around, round, round. We talked about the idea that the force along the string is acting toward me, right? The rock is really accelerating toward me. If it weren't, it would go somewhere else. But it keeps pointing toward me all the time, huh? I mean, well, that's what's happening here, too. The moon is being... But if you lived on the moon, how about the moon types? What do they see? Hey, no, honey, the moon is the center of the universe. The Earth going around us. Who's going around who? We're both going around each other. Now, you guys think the Earth is just like this and the whole universe going around you? Come on, okay? It turns out the Earth and the moon going around each other. A common center of gravity. The common center of gravity is still inside the Earth. Nevertheless, you can think of the Earth as accelerating around the moon. And this part, closer, accelerates more than this part and gets stretched right out. And then the solid Earth underneath, like this, rotating every day, huh? Every 24 hours. So what do? We rotate right into a high bulge of water. Then we rotate into a low bulge of water. And then to a high bulge again. And then low and high and low. And as this Earth turns, see? As this Earth turns, suppose the moon's over here, huh? Pulling. And there's all the time a bulge out like this. Hey, I'm simplifying, gang. I'm pretending that this Earth mass isn't here. That makes variations that are very important. We're really simplifying and consider the world to have no land masses that are going to get in the way. Just the overall idea of tides. A bulge on this side, a bulge on this side, and kind of shallow in here. So a person right here says, oh, wow, moon back here. The tide is high. Maybe it's about 1 meter higher than usual. Over here, wow, the tide just went out. The tide got low, okay? And back here, the tide got high again. Low, high, low, high, low, high. So how many high tides do we have every 24 hours? Begin with a T. 2. I'm sorry. How many low tides do we have every 24 hours? It turns out every 23 hours. You know why? Because the moon doesn't stay like that. The moon's kind of turning as it's happening too. See what I mean? So we can say, roughly speaking, 2 tides a day. 2 high tides and 2 low tides. It's kind of easy to see, isn't it? See? Stretched right out. See? If you're walking along the street and someone grabs your shirt and pulls it, and they grab this part and pull it, and this part and pull it, pull every part of your shirt the same, you'll move over, but your shirt won't get ripped. But you walk along the street and someone only pulls this part, and they don't pull the other part, you might rip your shirt. Because one part's being pulled harder than the other. And when you get a difference in pulls, hey, you're going to get a stretching effect. And that's why we get the tides. We get a difference in pulls of the moon. Do we get a difference in pulls of the sun? Answer begin with a Y, end with a P. Yep. Try it. Well, guess then. All right, the middle is a U. Okay, yeah, you do. You get tides from the sun as well. Okay, but the sun's so far away that it pulls just about the same on this side as on this side. Very, very far away, that difference is not so much. So the sun is pulling like mad, 180 times harder than the moon. But on near and far side, not so much different. Up close, yeah. You know what happened to that moon if that moon gets closer and closer to us? By the way, guess what has 2 bulges as well? Begin with an M, end with un. Try it. The moon. The moon got 2 bulges too. Okay? But the moon, of course, is the bulges stay fixed because it rotates just as often as it revolves. We talked about that last time. So on the moon, you don't see it going up and down every 6 hours. It just stays up. It's like a football shape. Okay? You know what happens when the moon gets closer and closer? The tidal forces get bigger, smaller, or stay the same? Bigger. And you know what happens when the moon gets too close? You get ripped apart, ripped to shreds. And all those shreds would just orbit around and spread out like a great big ring. Do you know there are planets where that's already happened? One begins with S, ends with turn. Do you know what it is, gang? Saturn, that's right. And another one is Uranus, Neptune, okay? Rings, moons that have gotten too close and simply got ripped apart into a whole lot of boulders and they're just all smearing around. That's what they are. Tidal forces can be enormous when you're very, very close to something. because the difference in pull between near and far might be greater than the force with which everything's held together with. Make sense? So tidal forces don't occur too much for long distances, but for short distances where the difference in poles is a lot, the tidal forces can be enormous. We don't get the same depth of tide every day. Some days the tide's higher and lower than others. And the reason for that is because both the moon and the sun are pulling at the same time. See, if I have the moon pulling here, and I have the sun out here pulling in the same direction, that's going to make these bulges even more. The sun contributes about 1/4 as much influence as the moon. I mean, it's still as big, okay? So when they're lined up, you get extra high tides and extra low tides. And it turns out that if the sun is on this side or this side, you get the same effect. It's just if they're lined up. Now, when the sun is on this side, what do we call that condition in the month, gang, when both the moon and the sun are on the same side, in between the Earth? Or when the moon is between the Earth and the sun? Do you know what we call that? We call it a new moon. Because at nighttime over here, these people here don't see any moon in the sky. You know, the moon's not out every night, gang. Sometimes the moon's out in the daytime, okay? And if it's exactly in front of the sun, what do we call that? Not an eclair. What do we call it, gang? An eclipse, okay? And then there's a shadow coming right down. You can bask in that shadow, okay? But usually it's not lined up exactly. And so we call it a new moon. You look up, you can't see it because you're looking at the dark side, see? And then with a night sky. But how about the other case, when the sun is on the other side? And here's the Earth in here. And then we got the moon over here. What kind of moon do we see, gang? Full moon. That's right. Because what's happening now, here's the dark side of the moon. Here's the dark side of the Earth. People up here look up and they see the whole moon full. You know? It's like the globe right here. If I play flashlight tag with you guys, and I put the globe up here, and then I put all the lights in the room out, blacking everything, okay? And I get in different parts of the room and shine my flashlight on the globe. Can you look at the globe and tell where the flashlight is? How about if the whole bottom of the globe was lit up and the top were dark room? Where would the flashlight be? How many say, oh, probably up there somewhere? Who? Stand up. Where would the flashlight be, gang? Down underneath, yeah? Yeah. And let's suppose you look at the globe and it's all lit up. Where's the flashlight? Maybe in back of you or in front of you, but along a line where you are, yeah? And if you see like a quarter of it lit up over here, just a quarter lit up, wouldn't I be back here maybe? This part be lit up? And you guys could see this part lit up in here? Yeah. So how the moon looks depends, of course, where the sun is. You know that. That's all we're saying. But when you have a full moon, how about the tides? Extra high? Answer begin with a Y. You got a friend, and your friend wants to go clam digging with you. You guys know what clam digging is? You ever eat clams before? You know where the clams come from? The tidal flats, the mud. You got to go out there and you got to dig them. You got to dig with a pitchfork, you dig them up. And you do that at low tide. And when the tide's really low, honey, you can go way out and get more clams. I used to do that a lot, okay? Clam digging. Let's suppose you're going to go clam digging, and you want to go at the right time of the month. And some guy says, hey, I know a good time to dig some clams. Saturday night's supposed to be a full moon. Let's go Saturday. We'll go dig clams at the time of the full moon. You are not too sure about that, so you consult with your friends who are knowledgeable about the wonders of the universe. And those friends are sitting right beside you now. And you say to your friend, gee whiz, would that be a good time to go digging or not a good time to go digging? Check. Would be the answer, gang. How many say, yeah, I think that's the time of the month to dig your clams, honey. That's the time I'm going to go. Show of hands. 1, 2, 3. Okay, how many say, no, I think I go to the time, honey, when it's got the least fullness. I'll go to the time of the new moon. Yeah, even Stephen, same thing. How about, no, I'm going to go when there's a half moon. Or, I don't know, I'm not too good thinking about such things. I'm here to take notes, gang. You tell me, I'll write it down, teach, and I'll memorize it, and I'm just looking for a C anyway. At the time of the full moon, how's the high tide going to be? Extra high? Are you going to go digging clams at the high tide? Or are you going to wait till low tide comes? You wait 6 hours later and you go, right? Now, should you go at the time of a full moon? How many say, yeah, that's the best time because you can get more clams because the water go way, way out and you get a real low tide? Show of hands. Only 2 people on this side of the room. I got something to invite you all to do Saturday night when you take your bath. When you take your bath, I want you to get in the tub and fill it up. And I want you to start sloshing the water back and forth. And when you slosh the water out in front of you and it gets extra, extra high, that's the time of the full moon, turn around quick and look behind you. And guess what you're going to find? Guess what you're going to find? Extra what? No, not high. Extra what? Extra low. And at the time of the full moon, the extra high tides got to be matched by an extra what? Conservation of water. There's only so much water to slosh around. See that? So the people back here, wonderful. You can kind of see that. If it's extra high one place, honey, it got to be extra low somewhere. Where'd the water come from? So yes, you go digging your clams at the time of a full moon. Right on. Because you have extra low tides. How many say, oh, maybe the tides are only confined to the water? It certainly couldn't be confined to the solid Earth itself because it's solid and rigid, right? Is the Earth solid and rigid? About like an orange. What's underneath the surface? What's underneath the skin? Huh? You been over the Big Island lately? Okay. It turns out it's all molten. And that moltenness, that molten part of the Earth, are parts of that molten part closer to the sun and the moon than other parts? Okay. So what's that going to do to it? Stretch it out. And you know what, gang? We have earth tides. Earth tides about 1/4 of a meter. Pucker back and forth about every 6 hours, just like the ocean tides. Tides in the earth. When do you suppose the highest probability is of getting an earthquake or a volcanic eruption? Full moon or some other time? Begin with F. Full moon. Why? It's extra stretched. San Francisco earthquake, 1906, very close to the new moon. And they're all lined up, extra stretched. You also get tides in the atmosphere of the world, okay? It's very, very low mass. They're not big, but they're there. And at the top of the atmosphere, we have all these ions. Ions are charged particles made by the cosmic rays coming in and splattering the air atoms. And what we get is we get a big flux of a change in the distribution of those ions with the position of the moon and the sun. And when you get a full moon or new moon, you get the deepest atmosphere, and that gives rise to what is called these changes magnetic tides. And these magnetic tides at the top of the Earth regulate the amount of cosmic rays that come down and hit us. Did you guys know cosmic rays are coming through the ceiling right now and going through you? And if they go through you without making a hit, who cares? But sometimes they make a hit, good or bad. It depends who it's hitting. If it's hitting you, it's not good. Okay, if it's hitting maybe some you don't like or what. No. These things going through us all the time. And there's a little blanket up there that regulates how much comes through. And guess when the greatest change from deep to shallow is? Guess what time of the month for the magnetic tides up there? When the moon is what? Begin with an F. Have you noticed that your friends are sometimes a little more weird at the time of a full moon? It might have to do with physics. Lee?
With the same effects, are they just about as strong when there's a new moon?
Yeah. Oh, new moon or full moon. When I say full moon, you're right. New moon would have the same effect. That's right. So the time of a new or a full moon, twice a month. Yeah. Do you guys be knowing what a blue moon is? This is not physics. A blue moon. I found out just 2 years ago what a blue moon is. Once in a blue moon. How many people know what a blue moon is? One. Well, I tell you what, if I told you, I would rob you of years later finding out what a blue moon is. Hey, son of a gun, that's what a blue moon is? How about that? Hey, man, that's pretty, I'll never forget that. But if I tell you in class, you forget it, right? Okay. See if you can find out from Lee or someone else. Hey, what mean a blue moon, honey? What's a blue moon? Is it really blue? Answer begin with an N. All right, N with an N and end with an O. Try it. Yeah, okay, good. But see if you can find out what a blue moon is. Not physics. Kind of interesting. Question?
Does that the same way like harvest moons are done? They're all orange?
Yeah, what's a harvest moon? Check that out too. Here's the Earth, gang. We stand at the surface. We're pulled down with a force. We're pulled down with a force of gravity. Between our mass, the mass of the world, the distance between our belly button and the belly button of the world squared, whip, boom, we get that force called our weight. Isn't that true? So we weigh, we have a weight because of the force of gravity. Let's suppose we went down inside the Earth and got right at the center in a hollow part. Make believe it's hollow. And right down here, how much would you weigh? A lot or a little? Answer begins with a... Check your neighbor. See if your neighbor will be onto this. Answer begins with a what? Not X, not Y, but Z. Zip. Honey, you got no weight down there. You know why? See, up here you're pulled like this. But you're pulled over here too. You're pulled over here. You're pulled in all these directions, you know. And all these directions pull you as if that we're all acting straight down. See? All those have a resultant straight down. But when you're down here, you're pulled to all this, you're pulled to all this, you're pulled here, you're pulled here. What's the net force? All these things combine to be what? Not a straight down, combine to be a zero. So in the center, you got no weight at all. Ain't that neat? At the center of the world, you're just bathroom scale, you wouldn't squash the springs. Because every part's being pulled in all directions, all the forces cancel out. How about you get halfway down? How about you dig a hole? And down here you put a bathroom scale on it. Would you weigh more or less? How many say, I'm not sure. I'm not sure anything in this world, but I think less. Show of hands. Yeah, everyone except the front row, except one. Okay, good. All right. The front row, you guys go up in the back next time, okay? See, the other guys got hands to look at, see? See, the back row types, you see the hands go up and they join the chorus, see? And you guys don't have that privilege, but I'm just kidding. Out, you'd weigh less. And why you weigh less? Well, you could say, well, if it's zero here and the weight up here, it's got to be in between. Or you could say, no, wait a minute, here's another way to look at it. When you're right here, you're being pulled down by all this ground over here. But you're being pulled up by all this over here. There's sort of like an unpulling being done. Isn't that right? Because we are attracted to every particle that makes up the Earth. So these parts here are kind of pulling us off the scale a little bit. And it turns out you would weigh less. But rather than draw a line like this and say we can have this cancel that, let me just give you the results of something really, really neat. It turns out there's another way to analyze it, and that's this. It turns out if you're halfway down right here, if you take this particular radius, which is less than the radius of the world now, and consider that ground, and take the mass of that ground, and the mass of you, and this distance square, that will be your new weight. And it turns out if you're halfway down, it would be half. Half weight. And you know what about all this ground here? You can throw it all away because all this stuff here doesn't pull on you at all. Not a net pull. Whenever you're inside a shell of uniform composition, that shell won't pull on you. You can just throw it out. And as you get the smaller and smaller mass, you see the weight keeps going down, 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 and finally when D gets zero, you're down at zero because there's no mass left. But it's the mass outside in that shell you can throw away. Let me show you a little argument for that. Here's a shell of uniform composition. I think you can see that in the center, any object in the center would have no gravity because it would be pulled in all directions equally. Do we see that? But what I want to do is I want to convince you that it would cancel out no matter where you are. And so what we'll do is we'll take a point that's about here, where this distance here is twice this distance. Do you think it would still cancel out this side and this side? What we'll do is we'll consider a solid cone of material. We'll call this M1. We'll call that D1. We'll call this M2 and 2D. Well, just D and 2D. Let's look at our equation. Let's have the equation guide our thinking, gang. The force over here would be our mass, say the mass of the point, okay, times M1 divided by D squared. That's this force. The force that's pulling over here, you might think it's more because it's more mass. Or you might think it's weaker because it's further away. And guess what one does to the other? See, when you're out here, it'd be twice as much this way, but twice as much this way. So how big would M2 be compared to M1? Do you see it's 4? It's 4. So M2 would be 4 times M1. That'd be like 4 M1s, boom, times your mass, MP, divided by this distance here, 2D squared. But when I take the twice the distance and I square it, what do I get, gang? Isn't it like 4D squared? And what do the 4's do? And what's this? The same darn thing I got here. So you know what? The pull here, equal. I just took a place that was easy because I got twice the distance here as here. But you put any distance you want and that will happen. Anywhere inside there, there'll be no gravity. There'll be no field region. Inside a shell like that, there'd be gravity-free region. There'd be no gravitational field due to this mass. It would cancel out everywhere. So if you ever get to a big, big hollow planet, the people on the outside of that planet would walk around as if all the mass were concentrated at the center. But down inside there, you know what they'd do? Just float around, honey. The gravity would cancel out everywhere. Very, very neat. So all we're doing over here is when we take a shell, all this cancels out. No matter where you are, get right here. All the parts to here will cancel all the parts to here for that shell. Really, really kind of nice. Let's take a case that sort of has a different result altogether, where we get closer and closer to the center. Let's take the case of a collapsing star. Let's suppose you're standing on this planet, star, or whatever, and here you are, and you got a certain weight. Let's just call it 1. That's your weight. You know what that weight is? That weight's the result of your mass, the mass of the whole star, divided by this distance square. Well, that distance is here to here. Okay? If this is a very, very massive star, you're going to have more weight. If you're more massive, you'll have more weight. If the distance is greater, you'll have less. What we're going to do is we're going to pretend that the star collapses. And we're going to see what will happen to our weight at the surface. Let's suppose the star collapses to become half size. Well, you're still at the surface. It still has the same mass. If you take a loaf of bread and squeeze it up till it's half size, it still has the same mass. It's just more compact, yeah? Okay, so we still have the same mass. You have the same mass. But the distance now is half as much as before. Will that make you weigh more, less, or stay the same? Well, we can kind of put the numbers in. Here's your mass, the mass of the star. But now the distance is half the distance that we had over here, but it's squared, isn't it? And can I write that like this? Can I write that like this? And can I write that like this? And isn't this what we had over here? So how much do we weigh at the surface there? 4 times as much. You would weigh 4 times as much when you get closer. On the Earth, you went half as close, and you weighed a half as much, burrowing inside. That's because the ground's pulling the other way. But over here now, it increases because you're getting closer, and there's no other mass pulling you off. So it increases. If you understand that, you can answer this question. Let's suppose this star collapsed, and you rode on it, and you're right here, and it collapses to 1/10 the size. So it's d over 10 for the radius, 10 times closer. How much more are you going to weigh? Check your neighbor. What's it going to be, gang? It turns out 100 times as much. You would weigh 100 times as much at the surface of that star. And it would become harder and harder to throw things into orbit. Harder and harder. Later on, we're going to learn that the surface of the Earth, to throw something away from the gravity, to escape the locality of the Earth and to outrun gravity, you would have to throw something at 11.2 kilometers per second. That's called escape speed. And we're going to learn that on the sun, for something to be ejected off the sun so it doesn't get sucked back in again, so it can outrun ever-present sun gravity, you'd have to go 620 kilometers per second. That's the escape speed for the sun. What do you suppose happens to the escape speed as it gets closer and more and more compact from the surface? Get harder and harder, you'd have to throw it faster and faster, or slower and slower? What do you suppose? Common sense. Come on. What's physics anyway, gang? Common sense, isn't it? Okay? And it turns out it would be, you'd have to throw it faster and faster. And let me just give you a little fact. If our sun collapsed to a size less than 3 kilometers in radius, and all the matter of the sun gets scrunched up to less than 3 kilometers, do you know how fast you would have to throw something from the surface of the sun to escape? 300,000 kilometers per second. That's the speed of light. Because for that particular configuration, escape speed would be the speed of light. And if it shrunk down any more than that, forget it. You can't move anything at the speed of light. In fact, light itself couldn't get out. You know, right now you look at the sun, it's nice and bright, yeah? If it got that small, I can't see it anymore. Because light itself would be sucked right back into it. The enormous gravitational field at its surface. And so we'd say it's just part of the black sky. We'd say it's a black hole in space. And that's what a black hole is. It's a star that collapses under gravitational pressure, collapses and becomes, and whereby it collapses to a point where the escape speed is the speed of light or more. Black holes. Turns out, gang, the astronomer types tell us that the sun will never become a black hole. It's simply not big enough, and the gravitational pressure wouldn't do that. So black holes are made of larger stars. But nonetheless, I've got an intriguing question for you. If our sun did turn into a black hole, what effect would there be on the orbital motion of planet Earth? Do you suppose you could grasp physics enough to not remember it, but to understand it? Let's try. Let's try. Over here we went from a weight 1 to a weight 4 to a weight 100. Isn't that right? Let's suppose over here, when this star collapsed down to half size, let's suppose we climbed a ladder. And at the top of the ladder, we put a bathroom scale, and we weighed ourselves with a more highly packed, dense star. What would you weigh up there when you're just as far from the center compared to here? What's your neighbor say? How many say same, same? Hey, that's right. You know why? Because your mass is the same. The mass of this is the same, and the distance is the same you had over here. So you wouldn't weigh more or less. Every part of your equation would be the same. These equations guide our thinking, gang. They tell us how to think. Over here, let's suppose you had a ladder. Get a longer ladder now. So you're just as far out from the center of this as you were to begin with. What would you weigh here compared to over here? The same. It's one more step, gang. Let's suppose this thing collapses to a black hole. And somehow, this is a thought experiment. You could put a ladder here. And you stand right there and you look, oh my gosh, a black hole. I read about those dudes. Okay? How's your weight going to be? How many say, this time not the same? Show of hands. How many say, no, I think the same? Show of hands. Yay, all right, my people. What's going to change? Not the gravity force, maybe the sunlight, you might get cold. Okay, but this doesn't change. This doesn't change. The way doesn't change. The only thing that changes is this mass gets scrunched up. But there's nothing in the equation that talks about that. And you know what's after the equation? A period. So whenever I ask you anything about gravity, the only things to consider are what are the masses involved? How far away are they? And that's it. And if you want a numerical value, then you'll have to put in the g, which will make this have the same units as this has. But that's it. So just, see what I mean? The equations guide your thinking. So it turns out if the sun turned into a black hole, everything would be okay. You know why the sun's round? You know why the Earth's round? You know why the planets are round?
Because if they were great big cubes, the corners would be pulled in by gravity.
Gravity pulls everything in until it gets round. The whole universe. It turns out the idea of gravity underlies our thinking about the universe. You guys hear about the Big Bang Theory? The idea that about 14 to 20 billion years ago, the whole universe was in one point, and it exploded out, huh? All flying out. Let's look at that in terms of the gravity bit here. Let's suppose here's the Big Bang. And all these pieces are flying out. Let's suppose we knock the whole universe into 4 hunks, just to make the thinking easy. If we can understand the simple examples, then maybe we can deal with complexities. Here's part of the universe here, here's part of the universe here, part of the universe here, and they're all flying apart. There's nothing else that exists, just this. And there they go.
Any force of attraction between these spaces?
How many say yeah? Turns out this will be attracted to here, this will be attracted to here, be attracted to here, and all these will act as if what? It'd all act right back down there. And this would act back down there. There'd be a force. These things would be going against a gravitational force. If that's true and the universe exploded, does that mean as time goes by, the universe will speed up? Or the universe would slow down? And it turns out the universe should slow down if this model's correct. And you know what? When the astronomer types look out in the heavens, they find out that the universe is slowing down. You know how they know that? Because they look at the things that are furthest to go, furthest away. And the thing that's furthest away is longest to go. You guys hip to the idea it takes 8 minutes for the light to get from the sun, right? When you look at the sun, you're looking at 8 minutes ago. You know that? And the next nearest star, Alpha Centauri, you're looking at 4 years ago.
So if you're looking at something way, way back there,
Looking at it way, way back in time, too. And they find out the things that are farthest away, longest to go, we're going faster than the things now. And that means the universe is slowing down. And furthermore, we find everything getting further, further away from us. It's like a balloon expanding, expanding, and everything's getting further away, slowing down, slowing down. Maybe what happens is it goes like this. And maybe it just keeps going forever and ever and ever. But maybe it might go. The whole universe. It's calculated to be about 100 billion years. That's called the oscillating theory of the universe. Every 100 billion years, another cycle. Now, take your diaries, take all the things that you like, take all your scrapbooks, okay? Put them in a nice lead casket, gang, and when it comes in and goes like this, how much is going to be left? Nothing. It turns out, I don't think we could leave a record. Everything would be, all the atoms, everything would be smashed right back down to elementary particles. And fly right out the other side, and the whole shebang go again. The whole dance, the whole story. And maybe it'll be a little different next time. Maybe not. And how do we know? We don't. And if there is, how do we know how many times it's happened? We don't. We think about these ideas. Those are big ideas, gang. What is going on with the whole cosmos? And there are people that, from day to day, work on those kind of things, and that's how they bring their lunch every day to work on. Those are the astrophysics and the astronomers. Really wild stuff. But when you start to think about these things that are far away like that, and big, it kind of humbles you. Because let's make a graph about what this whole thing is. Here we are right here. Here's the Big Bang. I'm going to just draw a graph right in this space here. This is a Big Bang. This is 50 billion years later, and 100, okay? When is the time that human beings learned how to control fire in this whole cycle? It's about here. When the graph gets about here, the human beings learned how to make fire. Where are human beings now? About here. Okay? Here's where we used to be. We were in the caves. And now we're like this. And we got this to go in this one cycle. I got a question for you. What will it be like? What will we be like when we get to here? What will be important to us? How will we relate to each other? And how will our perception in the scheme of things be? Like when we get to here. I've got a little mental exercise for you. Take a piece of paper and write down an operational definition of God. God, okay? God means many things to many people. Write an operational definition. By operational, I mean God is a being, a spirit, a consciousness who can do this, like who can read minds, okay? Who can be in all places at one time, who can da-da, who can do-da, da-da-da-da-da. Make your list. Honey, that being is what I call God, okay? Write that up. Take your list. Put it in a drawer. Wait. I speculate the day will come when humanoids could look over that list and say, yes, we can do all of these things. We all can now. If that's true, then what is going on? Think about that.